All right, everyone, let's get started. Good morning. Hope you had a good break. Bad news is we're back at it. But the good news is this is your last semester, right? So this is 491. I'm Jason Bakos. I think all of you have had me for 611, right? So you know the drill. This is a similar class to 611. We'll be meeting in here for lectures, and we'll be meeting in the lab for lab work. In 611, we always met at the beginning of the week in lecture and midweek in the lab. In this class, it's going to be a little bit more ad hoc. So if you look at the schedule, we're always scheduled for this room, but in reality, we'll be shifting back and forth between here and the lab. So at the beginning of the semester, we'll spend more time lecturing, and as the semester rolls on, we'll spend more time in the lab. I will announce where we'll be prior to class. I'll announce it on Blackboard. Does it make sense? Okay, so this is supposed to be a hands-on class like 611, so ideally we'll be in the lab most of the time, working on stuff. The lectures will be used just to convey conceptual material, kind of to fill in gaps that you need for the hands-on work. Okay, so if you look at the syllabus, everyone have a syllabus? Okay, section 1 has the catalog description. As I mentioned, you should have all taken 611 and also 313 and 240. The reason for that is we're using C. We're programming in C in this class, so that's why you need 240. And obviously there's a hardware focus, which is why we have 313 and 611. So I just talked about the meeting times. I'm going to announce where we'll be meeting prior to the class. I'll send an email out. I think most of you will know, though, because based on where we are in the course, it should be fairly obvious. But if there's any questions, email me. And of course, if you come here and no one's here, just go to the lab. Okay. I'm using Blackboard for the class. So I think everyone's using that for all their classes now. So we'll have the grades on there. You'll submit your projects on there. And I'll be putting announcements on there. I record all of my lectures, and instead of posting them on Blackboard, though, I post them on YouTube. So I have a YouTube channel. So if you miss a lecture or you want to hear me, you want to hear something again, you can go there. We'll have software installed for this class in 3D22, and I believe he's also got it in 1D43. Do you know that for sure?
I don't know. I've never been to 1D43 before, so I can't say.
But the hardware is in 3D22, so ideally you'll be in 3D22. The software we use for this class is the Arduino IDE, which you can also install on your laptop.
It makes things a lot easier if you're at home.
Yeah. In 611, we use the Quartus software, the CAD software. It's really hard to install on your laptop. But in this class, we're using the Arduino software, which is just an Electron app. So it's much easier to install locally. As I mentioned earlier, make sure you keep an eye on your email for announcements that I send out. And we'll be working in teams in this class, teams of 2, just like in 611 and 313. So you're going to want to find a way to collaborate with your teammate. Yes?
Sorry, do you have listed anywhere on the syllabus or on the Blackboard what, just to reiterate exactly what software we're using again for local development?
I don't have it on there, but if you email me, I can send you a link. Or if you just search Google for Arduino IDE, you'll find it on there.
You can install it in like 10 seconds. It's really, really easy. Don't worry.
Yeah. Yeah, it's gotten easier because they switched to, I think they're using VS Code now, right?
Yes, it's VS Code based.
Yeah,
it's not like a Java app anymore.
Yeah. Are you guys familiar with VS Code? Yeah. Yes.
Also, if you VS Code, it's called Platform IO. You can use that for
Oh, really?
There's also a command line tool called Arduino CLI if you want to use that too. That's what I normally use. But
What's Platform What is that?
It's a VS Code extension that you can use for Arduino development if you don't want.
Oh, it just turns VS Code into Arduino?
Basically.
Oh, oh, that's cool.
Pretty much anywhere, almost any of metal. I use it to get the
What's it called again?
platform IO.
Platform IO. And that's an extension? Okay. Yeah, so what he was saying is your vanilla VS Code can be used for this class as well if you download the Platform IO extension, right? That's pretty good. I didn't know that. Okay, so you'll be working in teams and you're going to want to find a way to share code with your teammate, which can be through GitHub or Dropbox. If you do it through GitHub, you should use a private repo. We don't have a way. Hold on 1 second. There you go. We don't have a way. We don't have a file system in this department where you can set up access control lists, to share through your home directory. So you have to do it externally. Does that make sense? Okay. So there's a textbook, which is basically one of those course packet things that instructors put together. It's available on cognella.com. If you're interested in that, it has basically the material that I cover written out in textbook form. Section 5 is the course learning outcomes. It's the boilerplate from the ABET syllabus. Section 6 is important dates. We have, you have a week to add or drop as usual, and spring break is March 10 and the week of March 9th, which covers the Tuesday, Thursday classes, March 10th and 12th. And then the final exam is May 5th from 9 to 11. Yes? I don't have the midterm date marked on there. In previous semesters, I gave midterms online, but I've switched to traditional in-class midterms. So we'll have an in-class midterm and final. But I don't know the date for that yet. Last day to withdrawal, March 30th. Is that right? Seems awfully late. Yeah. So it'll be, as usual, the midterm will be before the withdrawal date. So we have 2 TAs. One of them is Alex, right here. And the other is Soyash Singh. You might know Soyash. He usually serves as my 611 TA. He's not back from India yet, so he'll be here next week. As I mentioned, that we'll be using Blackboard for project submissions. I'll also be giving quizzes through Blackboard. There'll be 5 or 6 lab projects. And so we've got half the grade will be based on lab projects, and the other half on individual scores, the quizzes and exams. Okay, you'll share, whatever, both partners in each group will receive the same grade on each of the lab projects. So half the grade you'll share with your partner, and the other half will be individual. Okay. Section 9 has an approximate schedule. I'll talk more about that when I get into the introductory lecture. Section 10 talks about disability support. Section 11 is the syllabus change policy. We generally don't change the syllabus much in this class. 12 is the grading scale, which is standard grading scale. Section 13 is the academic honesty policy. You're expected to work with your partner in your group to collaborate, but don't share code between groups. And Section 14 is a new section I added, was just the generative AI policy. You can use generative AI like Copilot in VS Code, but use it as a tool and keep the following in mind. We're going to have group demos as we did in 611, and we are going to increase the number of points that is allocated towards the demo. So we'll ask you questions during the demo, just to ensure that you understand how your code works. And so that's part of the rubric, the grading rubric for each project. That makes sense? Did we come up with was it 20%, 30%?
I think it was, last year I think it was 10%.
Yeah, last year it was just 10. We're going to up it to 20. So we want to make sure you understand the code, right, that's in the project. So it'll vary by project, but each project has a rubric, and part of that rubric will be the demo, how well you can explain your code. Okay, so keep that in mind. And also, as I mentioned, we're going to have in-class exams, so you'll want to be sure you understand the material for those. The lecture and lab attendance policy is lax. I mean, as I mentioned, my lectures are posted online, so in principle, you could watch them there. It's obviously better for you to come in and see the lecture live. And then in lab, I mentioned that you can install the software on your own machine, and so you could meet outside of lab times with your partner and work on it. The hardware is to be kept in the lab, though, because we have a limited number of boards. But you can work on code without having a board. You can start working with your partner outside a lab if you want, and then just come into the lab to test. The purpose of the lab meetings is for you to be able to ask questions. So we have 2 TAs and myself, which is pretty good for a course this size. So you can get a lot of individual attention and ask questions. Yes?
You may have covered it, but for the approximate schedule, weeks 7 through 11, was just project work? Like, is that a project, or is that?
Yeah. The course is it's kind of the opposite of 611. 611, we spent more time at the end of the semester covering concepts, and more time just doing projects at the beginning. Whereas in this class, it's kind of reversed. We spend more time at the beginning covering concepts, and more time at the end doing lab work.
Were all like 5 or so of the projects they did in those weeks, or?
No, you'll work on the projects throughout the whole semester. Yeah. Okay, so group sizes of 2 are preferred. You can work by yourselves if you really want to, but you'll be at a disadvantage because you'll just be one of you working on it. Because the expectations for 1-member groups is the same as for 2-member groups, and we don't allow 3-member groups. We have some policies for projects there in section 17. Projects must compile to receive partial credit. So grading these projects is, as you might imagine, pretty difficult. If they don't work, it's hard to figure out how to assign partial credit to something that doesn't work. But at the very least, you have to make sure that your code compiles, to receive any partial credit. Only 1 member of each group uploads the project to Blackboard, submits it on Blackboard. And we maintain a spreadsheet that keeps track of the groups. So I'll ask you on Thursday to email me your partner names, and then I'll record those in our grade spreadsheet. So we know what the groups are, and so even though only 1 member of the group submits, we assign the grades to both, right? We can figure that out. You have to submit your project on Blackboard by the due date, and the late penalty is based on when you upload to Blackboard, but you don't receive a grade for it until you demo. So you could demo it after the due date without any penalty, as long as you submitted it by the due date. So it's the same rule as in 611. The reason we do it that way is because we generally prioritize answering questions in lab over group demos. So if you're ready to give a demo, you may not be able to give it right away because we're answering questions. That make sense? So as long as you submit it on time, you're fine as far as the late penalty goes, but there may be a delay in assigning your grade if you wait too long to demo. Let's see, there's a cutoff date. Oh, sorry, you have to submit by 11:59 p.m. on the due date to receive full credit. I've changed the late penalty a little bit. It's a 7.5% late penalty for each school day, so that doesn't count weekends and holidays. And it's limited to 45%. So if you submit it more than 6 days late, then you'll have a 45% late penalty. And then the second paragraph there just talks about that the late penalty is based on when you upload the Blackboard. You can only submit one version of each project. We don't allow resubmissions. We learned that through experience. And there's a cutoff date of April 23rd, which I believe is the last Thursday of the semester, right? So that's the cutoff date for submitting projects. You can still demo them after that, but that's the last day to submit. Any questions? Oh, there was a typo too on page 1. This is if you look under section 2, this room is 2A31, not 3A31, right? Okay, but you all figured that out. All right. So this class is about embedded cyber-physical systems. You all know what an embedded system is, right? You took a course on embedded systems. So an embedded system is a computer that's designed really just for one purpose, one application. And so its hardware and software are optimized for that purpose. So, even though, the computer inside a Tesla is more expensive than a high-end gaming machine, you obviously wouldn't be very good to play Overwatch 2 on the Tesla computer, right? It just wasn't designed to do that, even though technically you probably could. Cyber-physical system is kind of just a fancy word of saying microcontroller. When I was a kid, they called them microcontrollers. It's when you have a computer that somehow controls the physical world. And it does it through sensors. So it uses sensors to measure the state of a physical system. It's usually called a plant. In the electrical engineering department, they call it a plant. And what you're measuring is something called a process variable, right? So it's some kind of information about what the state of the system is, and then you have outputs that typically will connect to an actuator of some kind, which is when the system is assigning a value to what they call a manipulated variable. And so through the sensing and actuation, the computer can influence the physical world in some way. So this was originally designed, for industrial manufacturing and things like autopilots on ships. But nowadays you see these, everywhere. Drones and self-driving cars, autofocusing systems on cameras. Those are all cyber-physical systems. So that's the focus of this class, is to consider both embedded systems and cyber-physical systems. Okay, so there's a few things. I think Rasha might have already covered this in 313, but designing embedded systems and working with embedded systems is different from, desktop computers and laptops, which is what you spent most of your time using in the program. There's some weird design challenges. You often have constraints of some kind, volume constraints and power constraints. And in the case of cyber-physical systems in particular, you often have power constraints. Typically you have, they're powered off a battery or they're mobile. And computers have this caveat where their computational performance scales with the power. So, the power envelope. So if you want more performance, they need to consume more power, right? So you end up with kind of this spectrum of very lightweight systems that are technically computers. They're Turing complete. They can solve any problem that any other computer could solve at any scale. But they use very little power and they have very little computational throughput. So the example I have here is this, like this electronic greeting card thing. And then as you move up the spectrum, you have systems that have more performance, but they use more power. So the reason we talk about this is because in this class we're going to use a very lightweight processor. It's designed for, you know, applications on this side of the spectrum, right? Very lightweight type systems. So it's not very capable. It can't run Linux, which is kind of, in fact, all the programming we do is just bare metal programming, basically. You write code that executes directly on the processor. So you don't have the benefit of things like, segmentation faults, right? If your code crashes, it just kind of just bricks this processor, right? There's no dump that you can inspect with GDB, right? There's no crash dumps. There's also no virtual memory system. So, you know, you're kind of programming at a very low level. Does that make sense? Now, one of the interesting things about that is these lightweight systems use very little power. You can have processors that use, you know, like milliwatts, which is pretty impressive, until you find out that the lighter weight system you have, the least power efficient it actually is. Because computer systems can take advantage of economies of scale. So it turns out that, for example, if you take like an Arduino, you know, it uses 20 milliwatts and can do, I have the performance here expressed in mega or flops per second, floating point operations per second. Now, normally people don't do floating point code on an Arduino, but I did that so I can compare it all the way up to like a supercomputer scale. So like an Arduino might be able to do, like I calculated by hand, kind of back of the envelope, that it could do 200 kiloflops per second in terms of floating point throughput, uses 20 milliwatts. And so when you calculate the energy efficiency, you're calculating, you know, throughput over watts, right? How much computational performance you get relative to the power it consumes, which both of those terms, the denominator and the numerator, both have per second in them. So what that really amounts to is the amount of, you know, joules per operation, essentially. Joules per flop is what that reduces down to. But if you compare that to, say, a Raspberry Pi, the Raspberry Pi uses 100 times more power than Arduino, and it's like 150 times faster than an Arduino. So you might think, well, that's power inefficient, but actually it's not, because it's like 200 times more power efficient than an Arduino. It's just a consequence of when you scale up the size of a system, use more power, but it ends up becoming more efficient because it takes advantage of these, you know, economies of scale. So if you go all the way up to like a supercomputer, like the Summit supercomputer is a 200 petaflop. They have an exaflop now, as they have machines now that are this is a little out of date, 5 times more powerful than that. But that's a 10 megawatt machine, and it turns out that it's actually 10 times more power efficient than a Raspberry Pi, even though, you know, you're talking about a megawatt type machine, a huge supercomputer, right? So, but unfortunately, you know, when you're working with constrained systems like we do in this class, where you want to embed intelligence and, you know, clothing or small drones and that kind of stuff, you have to stick with these, you know, lightweight systems that are actually quite power inefficient in terms of their processing, and also they're you know, you generally are programming at a very low level, right, without the benefit of Linux and a very tall system stack. Okay, so in this course, just to give you a brief history of this course, I started teaching this back in 2020, and originally this was CSCE 371, Systems Engineering. We had an ABET visit. ABET is the accreditation agency that comes down and accredits our program. And they said that we need, you know, more hands-on courses and more lab-based courses. So we morphed 371, which used to be just more of kind of like a math class, basically. It was very conceptual. We morphed it into this class, and I took over. But as I developed the class, I involved students quite a bit, undergrad students, to help me develop the material and prototype tools and boards and projects and that kind of stuff. And so originally, we were targeting that 8-bit microcontroller, the Atmel 328P, which is, I think, is probably the most common Arduino processor out there. So we developed some infrastructure around that and some teaching material around that. But it turned out that was a little too lightweight, it was kind of a joke that you couldn't do much of anything with that at all, except for some really trivial stuff. And then, we had COVID, where I had to kind of redevelop the course and just teach it purely conceptually, just with topics. And then after that, we switched back. So this was the Atmel 328 board that we used. It was this Metro board from Adafruit, which was a pretty neat board. But like I said, it was just a little wasn't quite capable enough. Once we came back from the COVID shutdown, we started using the FPGA board, the same one that we use in 611 and 313. And the advantage of that was that we could do hardware-software co-design, which I thought was pretty neat. So you could write software that runs on the Neos processor like you do in 313, but then you could also design Verilog components that would serve as I/O modules. And put those on the FPGA, kind of like you do in 611. So it kind of combined 313 and 611, and you could build, specifically, one of the things we did is we created a pulse width modulation circuit for the FPGA, and we interfaced that with the Neos processor. So in essence, what we did there is we kind of went through the process by which people go through to design chips like the one that we're using in the class now, the ESP32, right? We got to actually do the hardware design. But I had some pretty bad feedback on that class, because students in this department, I found, really don't like the CAD tools, the Quartus design tools. And when you start doing really advanced stuff like hardware-software co-design, they get even more touchy, hard to use, temperamental. So yeah, the feedback was pretty bad on that. We taught it like that for a few years. 3 semesters, so spring 22, 23, and fall 23. And then last spring was when Alex came on board, and Alex and I changed things up again. We decided to ditch the FPGA and go back to an Arduino type, chip. But we didn't want to go with this 328P. We wanted something a little heavier weight, something that's a little bit to the right on the spectrum, with the power performance spectrum. So we chose the ESP32, which is, I think it's gaining in popularity. I think it's becoming, I remember when my old student, Charles, and I started looking at that, actually it wasn't even the ESP32, it was the ESP 8266. Yeah, it was a previous version of it. And people use that only because it had onboard Wi-Fi, And in fact, what they used to use it for was just for the Wi-Fi. So you'd use it basically as a network interface to the Wi-Fi. And you'd still use something like this as your main processor, and then use the 8266 as the Wi-Fi chip. Not many people at that time, I don't think, were doing general purpose programming on the ESP. But now they do. And so we switched this ESP32, which is the next version of the 8266. And it's a 32-bit processor, unlike this guy, which was an 8-bit processor, and 200 megahertz. So it's got 2 cores. It actually does run a very thin operating system called FreeRTOS. It's not like Linux, where you get a prompt. It's more of a library that you statically link in with your code, but it provides some services and hardware abstractions, which are nice. And we'll use those later at the end of the semester in the last project. And it has Wi-Fi and Bluetooth, and I think it has more I/O than the 328P. So it's a nicer processor. So originally, we bought these modules. So they have these dual inline, I don't even know what you call this. It's like a little circuit board with headers on it, right? So you can buy these off Amazon. And it's really small. It's smaller than a stick of gum. And it's basically just big enough to hold the ESP. And so Alex designed this white circuit board that's I have it with me here. So Alex designed a circuit board that accepts the ESP32 module, right? It's kind of like a, you know, I don't know, carrier board or base board, right? Which is kind of neat. This is kind of the same concept that they use with the Raspberry Pi. What do they call the Raspberry Pi module that you can stick on a
Like
bigger?
hat, Raspberry Pi hat.
No, it's like the system on module. There's a version of the Raspberry Pi that instead of having its own independent board, it's just a module that's designed to plug into a bigger board like this, like an expander. Compute module, yeah. Yeah. So basically, we designed this bigger board, and that allowed us to hardwire a bunch of peripherals on here that you can use. So we had a speaker and some analog circuitry and LEDs, and then there was a sensor here, an IMU, inertial management unit sensor. So we used this last spring, and it worked out pretty well. I got some good feedback on that. But we've improved on this now for this semester. We've now switched to this board. And so instead of using the module, instead of having a discrete module, like a, you know, I don't know, subboard or whatever that plugs in, this board is fully integrated. So the ESP chip is actually soldered, the raw ESP chip is soldered directly to this board, as well as the sensor. So this IMU is also a separate module that you could pull out. Now everything is integrated into one board. And the other main beef I had about this board was we were using the original ESP32, which didn't have debugging capability. There was no way to debug your code, aside from doing the ridiculous print debugging, which is, in my opinion, just retarded. I hate that, right? There was no way to actually stop your code in a debugging environment and spec memory and variables, right? Like adults do, right? So we updated the ESP32S3, which has a built-in debugger, so you can debug this thing now. And that was a major problem in lab because the code, as I mentioned, we're using very low-level code where you have to flip individual bits inside these peripherals. And if you get anything wrong, if it's not perfect, if you're off by 1 bit, nothing works. It just sits and looks at you, right? And so when we get questions in lab, like, why doesn't my code work? It's like, well, I don't know. I can't tell from looking at it. There's no way to tell what's going on. The only thing you could do is basically introduce 100 print statements and print out binary codes to try to figure out what's going on, which was obnoxious. This way, we can actually debug this thing. You know, you can actually stop it and see exactly what's going on at any moment in time, which is nice. The other thing I really liked about this board was we put these individually addressable LEDs. So there's these things, they used to call them neopixels, but I guess they're just kind of generic now. There's these LEDs that have, 24-bit color, right? Which is 16 million colors. So each of these LEDs have 16 million unique colors that they can light up in. And the really cool thing is that they're connected in series, so they're scalable, right? You can connect as many of them as you want. And, but we only had 5. And I was like, well, man, what a missed opportunity. Like, you could have as many of these pixels as you want, and we only put 5. So on the new one, we've got 100. And the cool thing is that these versions, the versions that we had on this board were like these big ones, right? We switched to the tiny ones now. So we have a tiny, this is literally like almost like a micro LED array. But it's only, you know, it's still only 10 by 10, so 100 pixels. It's not big enough to become your monitor. But it is big enough to actually play. Alex actually wrote code that plays like videos on it, which is kind of neat. And they're really bright and colorful, so I was pretty happy with that. And then we also beefed up the audio version. So we had some kind of a primitive audio amplifier circuit on here, and we've improved that on this one. So this is the new board, and this is actually Rev 1. Alex found some bugs that we're going to fix, and we're going to get another batch of these made, and this is the board we'll use. That make sense?
One other change I made is we switched from from micro USB to USB-C because some people were having the USB ports just off the board last year.
Yeah.
So I switched to USB-C, and so that should help as well.
Yeah, these modules had the USB connector was really delicate. And so, so I mean, now ideally, the way this class would work is you would design your own board, right? But we haven't quite figured that out yet, how the logistics of that would work. Because, you know, I mean, in particular, how we'd grade it, right? I mean, and then, of course, you have to deal with the turnaround time because they have to go out and it takes a few weeks to get these made. But, you know, hopefully at some point we'll just make our own boards. Everyone will build their own board. But at this point, we're just going to give you a board to use. Now, like I said, we only make, how many we get, like 30 of these done?
Yeah.
So even though they're small boards and they're not nearly as expensive as those FPGA boards, but we still have a limited number. So we want you to keep these in the lab. Okay, so that's the class. So topics-wise, when it comes to cyber-physical systems, possibly the most important conceptual aspect is how software talks to hardware, right? So originally, when we were working on this class, originally we were calling it SHIC, S-H-I-C, Software Hardware Interfacing course. We wanted to focus mostly on hardware-software interfacing, and we still do. We still spend like maybe a third of the semester on that, right? And the reason is because you don't really cover that in our curriculum, and it's important in embedded systems. So do any of you know how software talks to hardware, communicates with hardware? I mean, obviously you use it in your programming classes. You can print stuff to the screen, right? But how does that actually work? How do you print something to a monitor? How do you print to a printer? How do you talk to USB? How do you communicate with a mouse? Does anyone know? Yeah, but I mean, how does it, like, so you guys learn, like when I was in school, I took computer architecture and they said, okay, well, there's 3 types of instructions. Then software is comprised of instructions. And there's only 3 types of instructions. There's load stores, there's number crunching instructions like arithmetic and shift and comparison and that kind of stuff. And then there's branch and jump instructions which control the flow, right? That's how you implement loops and if statements and procedure calls, right? So then I got out of that class and I was like, okay, I think you're missing something here. I mean, I can write software that talks to memory with load and store instructions, but how do I talk to a printer? Like you guys forgot to mention that part. No one talks about that. And when I was in school, they pretty much said, oh, that's a driver. That's out of scope. You couldn't handle that. That's too complicated. Drivers. And I was like, how do you write a driver? Like, how's that work? And so no one ever explained that to me when I was in undergraduate school. And no one really does even now in our program, right? So it turns out that the way it works is they kind of lied to you in computer architecture. When you issue a load or store instruction, you're not actually strictly just reading and writing to memory. You also have special memory address ranges. And I think you guys covered this a little bit in 313, or at least you should, if Rasha still teaches it the same way I did. You have these things called I/O bases, I/O ranges, which is when if you store to a special magic address, and that magic address is usually something that has to be physically baked into the hardware. It's not changeable, it's not programmable. Basically, these addresses are fixed. So it doesn't matter if you buy an Intel motherboard or you buy an embedded system like the one that we use. You have a repertoire of these address ranges, and the only way to get those is from the user guide, and you can't change them, you're stuck with them. And when you boot Linux up, Linux becomes aware of these address ranges through something called a device tree, which is a separate file that's read when the kernel comes up. To boot Linux, you need 2 files. You need a kernel and a device tree file. Those special addresses are inside that device tree file, right? But basically, these addresses are physical addresses where if you write to them, you're not writing to memory. You're actually bypassing the memory, and you're going to an I/O device, some kind of a peripheral. And if you read from those address ranges, you're not reading from memory, you're reading from a device, directly from a device. Yes?
Would this be considered like SRAM?
No, well, maybe. They're usually referred to as registers, control registers and status registers. But technically, I think physically, they're built with SRAM in the peripherals, I think, generally. So each I/O device has these control and status registers, which is kind of an antiquated term because originally a control register is something that you would write to with a store instruction, and it would be an output to the device. And a status register would be something that you would read from, you'd load from, and it would be an input from the device, right? So if you have a mouse, you're basically just loading, you're constantly loading the status register for the mouse to have the mouse tell the software what it's doing, right? How it's being moved, right? And likewise, if you're sending data to a frame buffer, like a monitor, you want to send data to your GPU, then you're writing to you're doing a store and you're writing to a control register, right? But nowadays, there's not really a distinction anymore because you'll have some registers, I/O registers, that you can both read and write to, right? And you'll find that in this class, we have a lot of them, where there's some of the bits within a single word are read-only and some of the bits are write-only, right? So the whole control and status register thing is kind of, doesn't really make any sense anymore. It's just I/O registers. Does that make sense? Okay, so yeah, that's essentially how software talks to hardware, is through the load store interface. Now there's some other mechanisms too, like you have, and we'll talk about them in class. There's this notion of an interrupt where because the I/O registers are completely controlled by the CPU decides when it's going to read and when it's going to write to these I/O addresses. The peripheral doesn't have any agency, like it doesn't have any way to get attention or tell the CPU it needs something done. And so there's also this mechanism called an interrupt where the peripheral can try to get the attention of the CPU, but then after that point, the CPU then has to go and do these I/O transactions, load and stores, right? And then there's also, finally, there's a third mechanism called direct memory access, DMA, which is for high-speed peripherals, where the CPU has another chip that does bulk data transfer on its behalf. Because when you have to load and store, you can't do that at a very high speed, right? Your effective rate is very low, by having the CPU have to shuttle things through load and store instructions. Okay, so we'll talk about that stuff. So that's a big topic that we want to address. Another is protocols. So there are standard sort of dialects, languages that peripherals can communicate in. And there's a big spectrum of those too. There's low power, low performance ones like SPI and I2C, which we'll cover in this class. And then you've got, on the other side of the spectrum, you've got very high performance ones like PCI Express that are very fast, but generally not used in low power systems like the ones that we're targeting. Although the Raspberry Pi kind of sits in the middle. The Raspberry Pi it's a single board computer, but it actually has PCI Express, although just I think one lane, right? Nothing crazy, but we're focusing in this course on that kind of the low power kind of lightweight processors that use relatively slow I/O protocols. So we're going to cover those. So let's see, I covered all that. Oh, and also control theory. So I mentioned that in cyber physical systems, the CPU is controlling the physical world. How does it do that? Generally speaking, you use a closed loop control. So you read your process variables, you interpret them somehow, and then you write the manipulated variables, right? You go in a loop, right? It's a closed loop control. They have a whole class on that in electrical engineering, which is Electrical 331. Some of you might have taken it or might be taking it now. Most students don't. We had a few last spring that were taking it, which really surprised me. But that's it's math class. There's no applied stuff in there. Mechanical engineering also offers a class called Controls as well, which is a redundant class that covers exactly the same topics, but it's more applied, I think, than the electrical one is. But anyway, you could take a whole class on that. In this class, I'm just going to have 2 lectures on it, just to give you a taste, just to give you an idea of how it works. I don't want to spend too much time on it, but if you want to design a drone that flies, you have to understand control theory, and so we'll talk about that. And then finally, real-time scheduling, a real-time system. So another aspect here is whenever you design a control system, it has to its processing has to keep pace with the physical world. So there's this notion of a time step. You have a time step which determines what the cadence is of updating the manipulated variables, reading the process variables and updating the manipulated variables. Your processor has to be fast enough. It has to be guaranteed to be fast enough to achieve a certain level of performance in order to guarantee stability in your control. And so that's kind of a big deal, especially if you want to use one processor to control a whole bunch of things, where you're having to time multiplex the processor, right? So it's not as if, it's not like these control algorithms require a lot of workload in terms of numbers of multiplies, right? They're not like machine learning where you're doing millions of multiplies, right, to do a forward pass. They're relatively cheap, but you might have a robot that has, multiple servos and legs that are all being controlled simultaneously with one controller processor. And so you're having to subdivide the time. So you end up with all these different tasks, some of which are operating at different control steps. So you have a mixture. They're not all at the same period. They're operating at different periods. And so that becomes a challenge to guarantee that your processor won't blow any of the deadlines, any of the performance constraints you have for the system. And this is something that's quite crazy, because you would think, well, geez, with all the cyber-physical systems in the world, clearly Linux can do that, right? I mean, it can't. Linux is not real-time, not a real-time operating system. And Linux makes no guarantees whatsoever about bounds on execution time for any task. And no one thought to ever even put that into Linux. Well, there's been some work on it, but there are some real-time features, but it's not real-time operating system. And in fact, there are no free real-time operating systems. If you want one, you're going to pay a lot. They're all highly specialized and really expensive. Now there is a free RTOS runs on these boards, but it doesn't do the real important work of a real-time operating system, which is to guarantee that performance constraints are met. Like, in other words, you can't submit to it a list of tasks and ask it if it's feasible. It won't tell you that. It'll invoke the tasks, but it won't tell you, hey man, don't put this in the cruise control system because this is not going to work. There's too much work. Your utilization is above 100%. I can't do it. It can't do that. It's too dumb to do that. The operating systems that can do that are these ones that are expensive. And in fact, a lot of this real-time scheduling is kind of still an open problem, believe it or not. Doing scheduling in general is NP impossible, NP complete. It's an NP complete problem. So it's tough. It's a hard topic, and it remains to be hard. And there's entire conferences, academic conferences about this. So I want to cover that too. So those are really the three main topics we're going to cover in this class. We're going to cover like how to program these chips and stuff, but that's just vocational school stuff. In terms of the real academically rigorous part, it's going to be hardware-software interfacing, which involves just programming practices in bit manipulation and control and status registers, but also protocols. How you have handshaking and what the protocols are in which peripherals communicate. So we'll look at a few case studies there, and then control theory and real-time scheduling, and that's essentially all of the conceptual part. And the only reason I cover those is because they're important for embedded and cyber-physical systems, and you guys didn't get any treatment on this at all so far in the curriculum. This is the only time you hear about it, right? Unless you take, like I said, unless you took Electrical 331. Okay, and then aside from those concepts, we're going to do a lot of just hands-on stuff in the lab, right? All right, let's see, any question about that? All right. What do we have till 11:20? So we got some time. So I'm going to go ahead and get started then, talking about the first the first topic here, which is the programmed I/O. So I already introduced this. So generally the way this works, it's called programmed I/O. This is programmed I/O refers to the style used here to have hardware and software talk to one another. So the idea is that the whole idea behind programmed I/O is that the CPU is the master. The CPU is the only entity that can initiate communication between the software and the hardware, right? And the way it does it is ultimately it's through either pure load store instructions, like you learned about in 212, or some CPUs have special variants of the load store instruction for I/O. Anyone know why? Anyone can think of a reason for that? Why you need a special load or store for programmed I/O? So regular load and stores, hopefully you guys covered this in 212. I hope. Regular load and store instructions are connected to the memory hierarchy. You guys cover memory hierarchy? So there's a cache, right? There's a level 1, a level 2, and a level 3 cache, right? And the idea is that the memory hierarchy is a hierarchy of progressively larger but slower memories, right? And so ideally, from the software perspective, your performance for accessing memory would match that of the small memory, because the smaller memories are faster. But you would have the capacity of the larger memory, right? So you get the speed of a small memory and the capacity of a large memory. So it's like if you have an office where you have papers on your desk versus papers in your filing cabinet. You can get to papers on your desk faster, but there's less room for them. If you can get to papers in your filing cabinet slower, but there's more room for them, right? So ideally, when you access papers in your office, it's always according to the speed that you get from the table, but yet you still want to have the capacity of the filing cabinet, right? The problem here is that if you're doing programmed I/O, where you're using loads and stores to talk to peripherals, you don't want those loads and stores to go through the memory hierarchy. You don't want them going through the cache. Because if they do, when you write to a peripheral, you may end up just writing to the cache, and then that write transaction never makes it outside of the CPU to the peripheral, right? Does that make sense? So that's the reason why oftentimes you'll have a separate load that essentially says, I want to load or store, but not through the cache, because this is not actually using the memory, it's using the I/O, right? But from the programmer point of view, it's just a load or store. Now, how do you load or store in C? I mean, we know how to do it in assembly. You just write a load instruction. How do you do it in C? Well, in C, you're assuming you need the compiler to translate your C code to load and stores. How do you guarantee that it's going to do that? Well, one way is through a dereference, star. Hopefully you guys learned about pointers in 240, right? So a pointer is a variable in C that's a memory address, and if you use a star before that pointer name, that's called a dereference. And if you do that on the left-hand side of an assignment statement, it translates that into a store instruction, and if it's on the right-hand side of an assignment statement, it's a load instruction, right? Likewise, there's arrays too. So if you access an array in C, that is also essentially a dereferencing operation, right? And so depending on whether you put that on the left or right-hand side of an assignment determines whether it's a load or store. So basically what that means is if you're writing a driver for Linux where you want to have software talk to hardware, fundamentally what you're doing is just dereferencing operations, right? Of pointers where the pointer is a constant, and that constant is whatever came out of the manual for your hardware, right? So in a nutshell, that's how a driver works, right? Okay, so I mentioned that, so the CPU initiates that. Now on a system on chip architecture, like these days, a lot of the peripherals that you talk to are not actually on separate chips. They're on the same chip. You have this, because of Moore's law, the number of transistors that you can put on a chip is huge. It's so big that nowadays the CPU is actually quite a small part of the chip, right? And the other parts of the chip are all these peripherals. The peripherals can be I/O interfaces, like this is an SPI interface, right? You could think of this like a network interface that ultimately this goes off chip, but the CPU talks to the SPI peripheral, and then the SPI translates load and store instructions to the SPI serial protocol. Right? Does that make sense? Think of this as a network interface chip, network interface adapter, essentially, right? But this peripheral is on the chip, right? And then there might be something like a timer, which doesn't actually communicate off chip, but it has like a clock in it, right? So this is a way for the CPU to say, is it time yet? No? Okay. Oh, is it time yet? No? Okay. Is it time yet? No. That's really what you're doing here with the timer, essentially, right? This is like a wall clock. But it still communicates with that timer through programmed I/O. UART, again, is like a network interface. USB is another network interface. A lot of these are I/O devices. Some of them are just, like on an Apple M4 chip, one of these peripherals is going to be a neural processor, which acts like it's a processor. It doesn't go off chip. It just number crunches. It executes neural networks, but it's still a slave. So it basically responds, like the CPU sends workload to the neural processor on the Apple chip through programmed I/O. Ultimately through programmed I/O. It's how it initiates that, the NPU. The NPU does number crunching, and then it triggers an interrupt and tells it when the CPU when it's done, right? So when you do your Face ID, for instance, on your iPhone, that's what's happening, is that you're offloading work to a peripheral, but that peripheral is on the same chip, right? And all of that is done through this programmed I/O, and every one of these modules has an address range. And I mentioned these are magic numbers. Magic numbers meaning they're immutable ranges of addresses that you just have to accept as a programmer. Now, if you got an FPGA, you're designing your own hardware, like we used to do in this class, you can change these numbers. But when you have an off-the-shelf chip like the ESP32, you got to live with the numbers they give you. Okay? So you have to look. All of these come from the user manual. Which, by the way, if you've been on Dropbox, you'll see I've got a link to the technical reference manual for the chip, and so part of the reason you have to go to that technical reference manual is to look up these address ranges. Yeah, yes?
I understand the magic numbers part, but say for instance you had an address range for any of these peripherals that's like 10. Is that 10 of those peripherals, or is that like?
Oh no, they have 10. So yeah, that's a great question. So each peripheral has a different number of control or I should say I/O registers, right? So some of these will have a wide range. They'll have a lot of unique addresses associated with them. Some of them will just have one, right? Some of these peripherals you can get away with one, like literally just one register. Other ones have a ton of registers. Some of them have a lot of registers because they have an internal buffer. Like you can actually write data into these addresses to buffer inside of here, and then later on they'll send that data out through a serial interface or something. Does it make sense? So it just all depends on the peripheral. And that's the reason why here, by the way, you'll notice that in this example, I have different ranges here. So this USB peripheral has a range of 100 to 1FF in hex, right? This one has a range of 300 to 37F in hex, right? They all have different sizes. And so, so one of the questions I may, oh, and then by the way, the memory, the RAM will have its own range, right? And actually on these chips, on the ESP32, there's multiple memories. There's a flash memory that's internal, right? That's where you store your program. That's a non-volatile memory. But then it also has RAM, like any other processor. That's a volatile RAM. And the RAM and the flash RAM will have their own ranges. But all of these ranges come from a single global address space, right? This is all just one master, like you have one address space, and that address space is divided into these sections for all the peripherals and all the memories, right? That's the idea. So I might ask you on the quiz, for instance, I might say, what is the size of the USB peripheral I/O space? So to calculate the size, you have to unfortunately do some hexadecimal math, which is annoying. But you take the upper range, the upper limit, right? The upper address, the highest address in the range, which in this case is 1FF. And then you subtract the low range, which is 100. But you have to add 1 because it's an inclusive, it's inclusive, right? So the total size is 100 in hex, which is 256 bytes, right? Now, 256 bytes doesn't necessarily mean that you have 256 registers, because this slide, by the way, when I originally created this was when we were using the 8-bit Atmel 328P. On the 8-bit Arduino, every register is 8 bits. All the I/O registers are 8 bits. On the ESP32, they're 32 bits, which means that one register spans 4 bytes, right? So if it's 100 in hex or 256 bytes, the number of registers or the number of locations that you can load or store is that divided by 4, right? So it's going to be 64 I/O registers on a 32-bit processor, right? Now you might say, why do we have to divide by 4? Why not just make everything word addressable? I don't know. I don't know why they don't do that. For some reason, IBM in 1967 decided that all memory on every processor throughout all of time would be byte addressable. And they also decided that a byte was 8 bits. And now we've had to deal with this. It's like, having to deal with pennies. They're kind of worthless, right? Byte is too small to store anything, even a character anymore, right? So, but we still having to deal with this byte stuff. So everything is byte addressable, which means you have to do the math. You want to find out how many words, you take the bytes and divide by 4. Okay? Okay, so, but here's where things get even more complicated. So each word, each control word, I/O register, which is a word, right? But every I/O register in that range. So if the USB peripheral has 64 I/O registers, which is 256 bytes, each one of those registers is further divided into bit fields. In each of the not always, but usually. Each one of those registers will have bit fields associated with them. So, in other words, each control word is, you can think of it like a structure, like a C structure, like a struct, right? Or like a Java class with members in it, right? But each one of the components inside there is defined by a range of bits. Now, you guys know from 212 that, remember the instructions, in 611 and 212. Remember that an instruction is like that too, right? A computer instruction is a word, and there's different bit fields inside that word that mean different things. You've got the opcode and the register source 1, and the register source 2, and the register destination, right? The shift amount, the function code, that kind of stuff. It works the same way with control registers, except they're not instructions. They're treated like data, but they still have bit fields. So here's a really simple example that I just made up. So this is an 8-bit word. Again, in this class we're using 32 bits, but just for the sake of this example, this is an 8-bit word. And each one of these bits has a specific purpose. And in some cases, some of them are read and some of them are for write. Some of them are inputs and some of them are outputs. So, for example, you'll often see in a data sheet, in a technical manual, they'll show a table and they'll have bits. Each column is a bit field, and then the first row is what that's called, right? What the bit field is called. And then the third row, or the next row down, will be whether it's read or write. So in this case, we have a bit 6 is a read bit, which is a flag that indicates whether or not the peripheral is, in this case, on fire, right? It's on fire, it's a 1. If it's not on fire, it's a 0. On the other hand, bits 5 down to 3 is a 3-bit encoding of the temperature. So you read those 3 bits, and then you have to decode them to determine what the temperature is. Does that make sense? And then you'll have a write, some of them, you can also have read-write ones too. There's one called halt, which is bit 7 is halt. That's how I tell the peripheral halt. I have to write the bit 7. Okay? Now what's the problem here? The problem is that in order to access this, your software has to do bit manipulation. It has to be able to insert bits into specific fields, and it has to be able to extract bits from fields. That's difficult and error prone. Very, very error prone, as you'll learn when you write this code, right? But that's how these all work. This is the standard way that it's done. Does it make sense? Now, when I used to teach 212, students would always ask, why in the world do we have shift instructions? That is the dumbest thing. Like, what could that possibly be used for, right? And why do we have bitwise logical instructions? Like, why would we care about doing and or of individual bits? That's dumb, right? Well, it turns out this is why. You just never had to do it before. You never had to do bit manipulation. I mean, unless you're writing like if you guys were writing a simulator for, like, say, RISC-V, right? Think about it. Like, if you wanted to simulate a RISC-V processor, you would have to go into each instruction and take out the different fields, right? To figure out what the instruction, like if you wanted to disassemble an instruction, essentially, right? When you disassemble a machine instruction, you have to go in and grab fields and figure out what each bit field is. Well, it's the same thing here. When you interact with the hardware, you have to extract bit fields and set bit fields, right? So like I said, though, this is kind of it's not that hard conceptually, but when you have to do this a lot, it's error prone and kind of hard to debug. And this is what I was talking about, by the way, with the debugger. On our old board, we didn't have a debugger. And so, like, for example, in order to interact with the peripheral, you would have to read and write 27 different bit fields from 10 different registers. And if one single instruction was wrong, brick. You bricked it. It does nothing, right? Like, for example, in the audio project, it just wouldn't play audio. You'd write the code, you'd run it and say, well, I don't hear anything. Like, what's going on? Well, you're screwed. Have fun printing. Have fun writing print statements and then trying to go back and delete them all when you find the bug. So that's why the debugger, I think, is an important part of this course. Still going to be too hard, though, because even then, you have to stop it in the debugger and interpret a hexadecimal number as bit fields. The problem is that these bit fields are not always on multiples of 4 bits. And hexadecimal is a 4-bit multiple system, right? So if you have a situation where you need to find bit 7, you can't get that from the hex. You have to convert all the hex to binary by hand to figure out what bit 7 is, right? So that's, now keep in mind, though, that you only have to do this if you're writing the driver, if you're writing the driver code, right? So in this class, the original plan was to have you write all of the driver code. But by the time we got to the P-count project,
Yeah, P-count was there.
which was the lab,
Last lab.
Alex was disappointed because he said, like, they should write the driver code. And I was like, look, I don't want to write it anymore. I'm sick of this. So it turns out that the Arduino IDE has drivers for a lot of the, not everything. I think maybe everything. Oh, it has it for everything if you go to the ESP32 Expressif library, but not if you're just using strictly the Arduino. Anyway, there is software that exists for not automating, but creating an abstraction, a hardware abstraction. Functions that you can call as opposed to having to do bit twiddling, right? But for the first few labs, we have you do the bit twiddling just so you understand how it works. So when you go to work for Apple and they introduce a new neural processor unit, you have to write the Linux driver for that, and you would have to do bit twiddling for that, right? Does that make sense? Okay, so that's the idea. All right, so we're almost out of time here. I'll just start this out just to give you a taste. So how would you, here's the question. If I have an 8-bit register value, and this is in C, by the way, keep in mind that, see, here's the other issue too. I didn't mention this. In 212, you guys learned about shift instructions and logical instructions, right? And of course, you implemented them in 611. You actually implemented the instructions that do all this stuff in hardware. You just didn't really use the instructions that much, right? The problem is we're not using assembly. We're using C. So now you have to, when you do this bit manipulation, you have to write C code whose objective is to generate the assembly instructions that do the shifting and bitwise logical. So you have to understand how these operators work. So if I have an 8-bit value and it's in a variable called val, notice I have val, I have a variable name, it's not a register. So this is a variable. And I want to set bit 2 to 1. How would I do that? And I don't want to affect any, I don't want to blow away any of the other bits. I want to leave all the other bits the same. I just want bit 2 to be set to 1 by itself. Now you might say, what happens if it's already 1? I'll still overwrite it. I don't care if it's already 1. I want to set it to 1 whether it's already 1 or not, right? So how do I do that? There's a few different ways to do it. So I don't know if this is the best way to do it, but one way to do it is that first of all, you need a value of 1. You need a 1, you need a constant 1, which I assign to something called temp, right? Now you might say, why would you assign it to temp? You just use a literal. Well, because I might want to put a 0 there too, right? I don't want to use a literal, I want to use a variable because I want to be able to set, I want to just assume that it's a variable, right? Okay, so then I can take temp and I can shift temp 2 bits to the left. Why? Why am I doing that? Because I want that 1 bit. So basically when you put 1 in a variable, it right aligns it, right? It puts it on the right-hand side, right? So it uses 0 padding on the left, the 1's on the right. So if I need to get that 1 into bit position 2, I need to maneuver it into bit position 2, which means I need to shift that 1 2 bits to the left, right? So basically what that does is it just modifies the temporary variable to line up the bit in the right bit position. And then once I have that, I can perform a bitwise OR. Now, in C and in Java, and I don't know about Python, I don't know if Python even has bitwise logical operations, does it?
It's more annoying in Python, I think.
Yeah.
I don't do a lot of that in Python. I do most of that in C because I don't like doing it myself.
Yeah, in Python, this might be like a function you have to call. I don't know if Python has a built-in idiomatic primitive operation in the language itself to do this, but in C it does. Use a, well, I say OR. It's a single bar, right? Bitwise OR, right? And so you OR these 2 guys together, and what that's going to do is going to leave everything alone except for bit 1. If bit 1 were previously 0, it's going to flip it to 1. If it was already a 1, then it doesn't do anything, right? So you basically just OR these together, and now you've set bit 1. A shorthand way of doing this would be in C would be to say val equals val, or in this case I just have a literal 1. I take a literal 1, shift the 2 bits to the left, and I put this in parentheses. Why? Yeah, that's actually real important because in C, well, I've been burned by this. In C, the order of operations is, I believe, I got to double check this. I'm pretty sure this is right. It's going to do the OR before it does the shift. So if you don't put parentheses here, it won't work. It'll break the code, right? So I got parentheses here that shifts a 1 by 2 bits, and then I ORed in. So basically, it's like you merge this in the val, and then it'll set bit 1, right? Okay, well then we'll leave it there for now. We'll see you guys on Thursday back in here, okay? Not in the lab, we're meeting in the classroom.